আমি বললাম সরি নামটা পাল্টেছে hello
Yes, sir.
so am I visible
Yes, sir. Yes, sir. You are visible and
and
audible.
audible?
Yes, sir. Yes, sir.
Okay, thanks a lot for the background setup. So right in the beginning I am going to share one document in your presence.
Okay, sir.
So please আজকে দিনটা এটা cancel. Your internet connection is unstable. এটা ক্যান্সেল করতে হবে নিশ্চয়ই। এটা মাঝখানে করলে আবার গন্ডগোল হয়ে যাবে।
See, displaying. Yes, sir. It is displaying.
No, can you see the slide?
Yes, sir. Yes, sir. You can give as a work network.
What is that? What
you can
network?
The work network. Yes, sir.
Work network. Okay.
Okay, sir.
So now I have to give lunch.
It is already launched. You are already in the meeting.
But okay, just a moment. Yes. Can you? Is the screen visible?
Yes, sir. Yes, it is visible, sir.
It's handwritten in a very naive way. It's visible, right?
Yes, sir. Sir, if you can make some presentation, then it will be far better for the students, sir. Because I think the students are getting somehow distracted, hearing and hearing and hearing.
That's why you have this slide now.
Yes, sir. Yes, sir. Yes.
Okay.
Yes, sir.
That's why
Yes.
today we have these slides. Because I'm not familiar with and I am using this tab. Hello.
Yes, sir. Yes, sir. Yes, sir. It is okay, sir. Yes.
Actually, that is the problem in online mode. Unless this class has to be completely interactive. That
Yes.
is the problem. That is the problem. So and now you have only computer science and IT students. Do you have students from other branches as well?
Yes, sir. Pardon, sir.
Do you have students from branches other than computer science and IT also?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. We do have.
Very good. Very good. That's why you have noted I have titled this session as role of algorithms in problem solving. This is not design of analysis of algorithms, which is a conventional course.
Yes, sir.
And once again, thanks a lot for whatever disturbances we had again. Thanks a lot for doing this, setting up.
No, sir. No, sir. Actually, I have got the link, both links. Now I will send the link to the both.
Right. And from next week onwards, please carry on with whatever we have done today. Huh?
Yes, sir. As today, I will take the necessary things that is done today.
Right. And you can tell the students that now they will see that I'm using some slides today, but these are I do not use PPTs generally. I use PPTs only for conference and workshops. Generally, I'm saying generally. Okay.
Yes, sir.
So let me know. Should I wait for 3-4 minutes?
Yes, sir. Yes, sir. We have to wait 2-3-4.
So Dilip, can you hear me?
Yes, yes, sir.
Okay.
You are audible as well, and video.
Okay. So if not required, you can mute yourself also.
Okay, sir.
So, Prem, let me know when to start, huh? And
Yes, sir.
also, please WhatsApp me your number and just say hi, huh? So
I
that
was
every
about to
time
tell you, sir. I was about to tell you that.
otherwise, there is no reason to bother Shobdatta for everything. These are minor issues. Up to what time I have today?
Sir, you can take it. It is available, sir.
Okay, because I don't know, today I'm going to cover some very interesting problems. So it may take some more time. I'll try to finish it off
Yes,
in
sir.
1 hour.
As you can take to complete, we are able.
Okay. No, because sometimes you have some other programs scheduled after this. So I just.
So today we can go it, sir.
Okay. I have to shift it towards left. Can you do, it seems, right side of this slides, there are some pictures, mine and others. Can you remove that?
Sir, you can just click on the button. They are available. The buttons are somehow like minimize, restore at the
But I
top of
don't,
the.
I don't want to disturb. I actually,
The,
when writing,
the window that the photo are coming.
Mhm.
On that window at the top of the photo, you can see there is minimize button. 2-3 options are there.
Mute is there.
Top level, sir. Top level of the photo.
Oh,
At the
hide.
middle, you can click. Yes, sir. Yes, sir. Yes.
This one. So small active speaker video. I,
No, sir. No, sir. No, that one. Sir, leave it, sir.
okay. Now, can you see the entire?
So, sir, from outside, it is all visible. Not your photo visible. The slide is only visible.
Oh, so the slide is visible completely, right?
Full, yes, sir. Only we are able to see the slide and a short video of yourself only.
Okay. Like here you can see if I less than equal to SJ or the other part.
Yes, sir. Yes, sir. Yes, sir. Fully available.
Okay. So I'll begin once you give the green signal. And tell the students that they need not have to worry now as they see. I'll be using this kind of, these are handwritten. Since this is some kind of digital tab, the handwriting is very bad. I can tell you my handwriting is not that bad, but somehow it's legible.
Sir, it is okay, sir.
I can assure you that my original handwriting is not that bad, but okay, I have improved a bit over the days. And I have already given them the list of 4 books. At least 3 of them, each student must be accessible to each of the students. Mainly computer science and IT students. Coleman, Kleinbach Tardas, and Horowitz. So I can start, I believe, Prem.
Yes, sir. We missed it, sir. We missed it.
Because initial 5 minutes would basically be recapitulation of whatever I have
Yes, sir.
said
Yes, sir.
earlier. So
Yes,
if
sir.
somebody joins within next 5 minutes, he or she will not miss anything.
Yes, sir. We may proceed, sir.
Okay, good. Okay, namaskar and good morning to you all. Uh, at the outset, I will tell you, today's session is going to be a game changer in the series of sessions we are having in this course. I think today is the 6th or 7th program. Uh, I hope we all understood by this time the inner meaning of the title of this series of talks. Role of algorithms in problem solving. Role of algorithms in problem solving. And we strongly believe that this is essential for anybody, irrespective of his or her discipline, in family life, social life, personal life, professional life, everywhere. And the necessity has been amplified further because we are already in the era of artificial intelligence and machine learning. So it is from this perspective, this series of sessions have been designed. Today, we will explain our position with the help of several examples, which I believe you would also appreciate that these are very interesting algorithms, very interesting examples. And this is only the beginning. Henceforth, we will concentrate on numerous examples to establish our view about the necessity of having some working knowledge on algorithms. We can give an analogy like if you are in mechanical engineering or electrical engineering, always you have to take recourse to mathematical models. But a mechanical engineer need not have to be an expert in solving differential equations. But a mechanical engineer must learn the technique of developing the model. Model there means the differential equation. And then he can take help of numerous documents available in public domain for solving the differential equation. So they may use the tools. Okay. So to start with, I'll just make a brief recap because today we'll work on graphs mostly and some trees. So we have already said what is a set? Set is a collection of homogeneous objects, homogeneous entities, set of boys, set of girls, set of, okay, so set of boys homogeneous, set of girls homogeneous, we can say set of students also, then boys and girls come together. We can have set of Bengalis, Orias, Assamia, and then we can have a set of Indians. So a set is a collection of homogeneous objects. And a graph is a collection of nodes and edges. You see, we have this example here that we have a graph. Concentrate on the graph which is drawn on top of league, which has 1, 2, 3, 4, 5 nodes, and count the number of edges. So this is called a graph, a very, very important model or structure, which is basically the darling of mathematicians for hundreds of years. For computer science students, again, this is very, very useful. The idea is many problems, numerous problems, which can be converted to graphs, and then it becomes, and within graph theory, the solutions are available. If there is at least one path from, okay, we know that nodes and edges, sequence of edges make one path. Sequence of edges make one path. If there is a connectivity or at least one path between one node to any other node, any node to any node, then the graph is known as connected graph. If any two nodes have at least one path between them, then this is known as a connected graph. We can have parallel edges between two nodes. We can have self loops also. That means a node, a path, an edge starts from one node and then another node. But we have drawn one simple graph here. And if there is a direct edge between every pair of nodes, if there is a direct edge between every pair of nodes, then it is known as a complete graph. If there is a direct edge between every pair of nodes, then it is known as a complete graph. Okay. Now, if a graph is such that for any two nodes, there exists one and only one path, then it becomes a tree. You see what I have drawn above, knockout is a tree. And we can have undirected graph as we have drawn here. We can have directed graphs also when the edge will have direction from one node to another node. Clear? Now, if we have a complete graph, that means each edge is directly connected, each node is directly connected to every node, or for every pair of nodes there exists a direct edge, then it is complete graph. Now, if we have n number of nodes and e number of edges, n number of nodes and e number of edges, in a complete graph, what would be the value of e in terms of n? Here, each node will be connected to n minus 1 edges. So that will be valid for each of n nodes. So it will be n into n minus 1. But then each edge will be counted twice. So it would be n into n minus 1 by 2. In this case, we have 1, 2, 3, 4, 5 nodes. So if this is a complete graph, then what will be the number of edges? 5 into 4 by 2, that is 10. 20 by 2, that is 10. And since we are multiplying n by n minus 2, n minus 1, at least one of them will be even. So we are sure that it will be divisible by 2. On the other hand, if the nature of the graph is such that for any pair of nodes, there exists one and only one path, then it is known as a tree, the way we have shown by the side of the graph. And as a corollary, we can say that a tree cannot have cycle. A tree will not have cycle. And if the tree has n number of nodes, it will have n minus 1 number of edges. As for example, see in our tree, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Just see how many nodes are there and how many edges are there. And you verify yourself that the number of edges will be n minus 1. Simply speaking, these are graphs and trees. You have hundreds of books on graphs and trees, thousands of algorithms on graphs and trees. We will try to use some of them to explain the theme of our talk. Now, consider an example. And this is a brief recap. I had given the same example earlier. Say, think of a tournament like IPL. Think of a tournament like IPL, where you have, say, 10 number of teams. And each team plays with each other team. So how many matches have to be organized? If the number is very big and you want to compute it by hand, you will be in big trouble. So this is a league kind of tournament where we have n teams and each team plays with each other team. So if you convert it to a graph model, this is nothing but a complete graph where each node represents a team and the edge represents the match between two teams. So if we have 8 teams, how many matches? 8 into 7 by 2, whatever, 56 by 2, 28. Now, each pair of team plays twice, home and away. So multiply it by 2, that is 56. So without doing any hand or any naive brute force computation, just converting the problem to the form of a complete graph, we know how many matches have to be organized. Think of another kind of tournament. As it is going on now, I was watching yesterday a French Open, which is a knockout tournament. I was watching Nadal and whatever, Djokovic playing. So that is a knockout tournament. And what is a knockout tournament? There, 2 teams play each other. There is no draw. One team wins and the other team loses. The team which wins goes to the next round and the team which loses is out of the tournament. That is a knockout tournament. So, having given n number of teams participating in such a knockout tournament, how many matches have to be organized? Think, if it is 2, number of matches to be organized is 1. If it is 3, number of matches to be organized is 2. If it is 4, it is 3. So if you have n teams, you have to organize n minus 1 matches to find the winner. and it becomes a tree. The structure becomes a tree. So a league type of tournament can be modeled as a complete graph. A knockout tournament can be considered as a tree. If I have a very big knockout tournament, say 110, how many matches have to be organized? Straight away you can say it will be 109. You don't have to do or scribble in the paper and all those. Straight in -1. So these are very simple examples where a common problem for anybody is modeled in the form of a graph, and then we get into the solution. So it is the job of tournament organizers to convert the problem definition into a model, and it is the job of a mathematician or theoretical computer scientist to get into the result. Why is it n into n minus 1 by 2 in that case, n minus 1 in the other case? So that is the job of theoretical computer scientist and mathematician, but they may not be having domain knowledge. So the organizers who have sufficient domain knowledge and reasonable idea about these models, they have to convert their problem definition into such a model, and then consult the tools available, the results available to get the solution. So far, this was the job of a systems analyst or systems engineer. But with the evolution of technology, now every one of us has to have some knowledge about how to convert this a problem to a model. Okay, this was a very simple example. Let us now go further. Take another example. This is very interesting. At least I find it very interesting. So you see a graph. I have written independent set. What is an independent set? Here we have nodes 1, 2. Listen to me very carefully. This is very, very important. What are the nodes? 1, 2, 3, 4, 5, 6, 7. There are 7 nodes, and I can see some edges. Any subset of these nodes, we can assume. We can take any subset of nodes. So 1, 2, 3, 4, like that. 1, 2, 6, 7, like that. The subset of these set of 7 nodes, if chosen in such a way that no two of them has direct edge. Listen to me very carefully. If we choose a subset of nodes from these 7 nodes in such a way that no two of them has any direct edge, then we call that subset an independent set. Such an independent set with maximum number of nodes is known as maximum independent set. I'm explaining again. We have a graph here, 1, 2, 3, 4, 5, 6, 7, and we see there are some edges, like there's an edge between 1 and 2, but there's no edge between 3 and 4. So, of course, with 7 nodes, at the most, we can have 7 into 6 by 2, that many edges at the maximum. Now, out of these 7 nodes, if we take out a few nodes in such a manner, there is no direct edge between those 2 nodes, that subset is known as independent set. Independent set. If we have such an independent set with maximum number of nodes possible, then we call it a maximum independent set. In this example, we have 1, 4, 5, and 6. These 4 constitute the maximum independent set. Just verify yourself. 1, 4, 5, 6. And this is a very standard problem in computer science. It's a very, very complex problem. What I am saying, as a person working in any domain of life, if I have to solve a problem which I can convert it or which is convertible to the problem of independent set, my job is done. Then I consult a computer scientist because the solutions are available. I know what is the solution. I know what is the solution from there. But this is a very, very complex problem for theoretical mathematicians and theoretical computer scientists. And it has been proved that for sufficiently large nodes, large number of nodes, it is not feasible to get the optimal solution in feasible amount of time. But that's a different thing. Now let us consider some real life problems. The students probably say, some of you make a group and you want to make a trip to Europe, say n number of cities, and you want to cover as many cities as possible. As many cities as possible. Naturally, while making your tour plan, you'd like to plan your schedule in such a way that at no point of time, every consecutive cities you are going to visit, they are connected directly. Otherwise, we have to go by a different route and it will take more time. So for that matter, you need to know what are the airports. Rather, for each airport, what are the other airports to which it does not have a direct flight? Got my point? A travel organizer is planning a trip for a group to visit as many cities as possible in Europe and moving by flight. Since the objective is to accommodate as many cities as possible, the travel planner would like to plan the schedule in such a way that for every visit, they go always by direct flights only, to save time, cost, and okay. Can you convince yourself? This is a straightforward independent set finding problem. Problem of finding an independent set. In this case, you know, suppose you want to visit 1, 2, 4, 6. You will not plan to visit 4 immediately after 1. Because in any case, you have to go visit 2. So, 1 से पहले 2 जाना है, उसके बाद 4 में आना है. So, this tour planning under the boundary conditions are discussed is basically finding an independent set problem. But as I have already told, can you imagine if we have 100 such nodes, hundreds of edges, how difficult it would be, to find the maximum independent set out of that. In computer science paradigm, this is known as NP complete problem. And in fact, most of the graph problems are NP complete. For the time being, you need not have to bother about that. But the problem becomes extremely difficult when I am looking for some optimal solution. Here, optimal means maximum independent set solution. If I relax my criteria and saying that, okay, I'm happy if it's not the maximum independent set, at least it is close to maximum, it is acceptable, then it is easier to compute. So that is known as a satisfiable solution. Nowadays, computer science classes, when they have algorithm, the analysis and design, this notion of satisfiability is becoming more and more important day by day. Let us take another example. Say, again, the travel planner. They have advertised for, again, a trip to Europe. And depending on the number of applications, they're planning to have, say, groups of 20, 25. So they may go for 3, 4, 5 groups, depending on the number of applications. And the travel planner receives, say, 100 applications. So they have to separate them into different groups. Of course, some applications, they come with some the restrictions that they want to be in a family. Some of them, they say that I have to go with him. Someone say that I do not want to go with him. But beyond that, the travel planner also has some flexibility. Which application has to accommodate it to which application, to which group? What we will do today? He has social network. It is expected that nowadays, each of all the persons who have applied for travel, they have an account in Facebook or whatever. So let's consider Facebook. And they have also friends in that social network. Friends means with whom they chat. Friends means with whom they chat. And we can get the statistics depending, say, what is the frequency of chatting. So, what the travel planner would like to do? They would like to make the groups in such a way that the members in each group are more or less known to each other, or more or less they have some kind of homogeneity in their likings, dislikings. In social network, every node will have some static parameters. Whether they love football, soccer or not, whether they love singing or not, what kind of places they want to see, and all those. What they can separate out those nodes which do not have any kind of similarity or very little similarity, or who are not speaking directly. Got my point? Very clearly, if you think yourself, this problem is again, it can be modeled as independent set problem. You can have plenty of other such examples. You can think yourself. And for the computer science students or IT students, computer application students, not computer to that extent, I would suggest them to develop an algorithm and see how it works. Again, it's a very complex problem. At this point of time, we are not getting into the analysis of the algorithm, but we know the design to some extent. And think of at least, I have given 2 examples, at least one other example problem, which is solvable using independent set problem. Okay. Now let us have another problem, which is interval scheduling problem. What is that? Suppose we have a room or a building which is used for renting for organizing marriage ceremonies or some functions, organizing some functions. Very common. And they get requests from many customers saying that, yes, I want to book this room for 3 days, this and this. Someone say that I want to book it for 4 days. Someone say I want to book it for 1 day, something like that. So every request is characterized by start date and end date. We call start date as I and end date as J. I have only one such resource available with me. And I have got n number of, say, 10 requests. Some of them will conflict, obviously. Some of them will have conflict, obviously. So now suppose for the time being, my objective is to accommodate as many requests as possible without any conflict. I hope I could explain the problem. I have a resource to be shared by many requests. Each request has one start time, one end start date, one end date, I and J. Obviously, some of them will have conflict. My problem is to accommodate as many requests as possible, so that there is no conflict on the resource. So How do I mathematically define the conflict? If they have to satisfy, say, two jobs or two resources, rather two requests will be in conflict. If Fi is less than equal to Sj, that means finish time. The other way around. The condition to be satisfied so that two requests will not overlap. That is, will not be in conflict. If I is less than equal to Sj, that means finish time of ith job, is less than the start time of jth job. Then in job request, sorry, I should use the word request. Finish time of ith request is less than start time of jth request. Then I and j are not in conflict. Or finish time of jth request is less. This is the other way around. So this is the other way around, that either one has to be finished before the beginning of the other one, or you take it from the initial side that you have to start only if the other one has already finished. So these two are the, I'm not getting into detailed mathematical thing, and this symbol means for all I and j. So this is to be valid for all I and j. This is a very practical problem. We face it day in and day out. Now, here is the catch. Here is the interesting part. Now let us draw a graph. You see the example I have given there, these four in the last sequence, these four requests can be accommodated, and that's the maximum. That's the maximum. Now suppose, let us draw a graph like this. I represent each, listen to me very, very carefully. I represent each request as a node. I represent each request as a node. That means if I have total n number of requests, I will have n nodes. In this example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We'll have 11 nodes. To draw a graph, I need to have nodes and edges. Here are the nodes. So what are the edges? I take any two requests. If there is an overlap, I give an edge. I draw an edge. Again, now here I have 11 nodes, and I draw an edge between two nodes if there is an overlap. And I do it for all pairs of requests. And the graph is made. Now think carefully. If I compute the maximum independent set of that graph, what do I get? Clearly, I get the answer. Here are the maximum number of requests, which can be no two of which has any conflict. I hope you understand. Think yourself very critically. The real challenge is how to convert some problem, which is real life problem we face every day, to convert it to a model which is formal, and we know how to handle that problem, how to handle that model. Okay, another example of independent set. Again, you think of some other problem. Here the catch is, everywhere the catch is, to convert it to a graph, you need to have nodes and you need to have edges. Which one you consider as node and which one you consider an edge, and what you ultimately want. This is interval scheduling problem. Just a moment. Let us consider another problem. Say bipartite matching. Bipartite matching. What is it? This is called a bipartite graph. What it is? If you see, this is also a graph with the 10 nodes, x1, x2, x3, x like that. But the nodes are such that they may be divided into two subsets. Divided into two subsets, but they are in the same graph. So that is why this is known as a bipartite graph. Now let us consider a problem where x1, x2, x3, x4, these represents 5 jobs. y1, y2, y4, y5, these represents 5 resources. The jobs may be, you may consider that a human being also. That can be any job. And y1, y2, y3, y4, that may be machines, some resources. And we know some job requires some resources, and some resource can be assigned to some jobs. Each job cannot be completed, cannot be done by any one of these 5 resources. Similarly, each resource cannot be assigned to any one of those jobs. As for example, here, job x1 requires resource y3. Job x2, but at any point of, but they need only one resource. Then like x2, it can be executed by resource y1 or y2. x2 doesn't require more than one resource. They require only one resource, but that resource may be y1 or y2. But y3, y4, y5 will not work for x2. Just see x3, y2, y3, y4. x3 can be executed by any one of these 3 jobs. On the other hand, y3 can be assigned to only x4 and x5. The problem is very simple. It's not very simple, very complex. But now you can understand the problem statement. How can we come up? How can we come up with a solution where maximum number of such matchings can be accommodated? how can we sum up with a matching one-to-one in such a way that the maximum number of matchings can be accommodated? Can you give some brute force kind of scenario here? X1 goes to Y3. Think yourself. Can you do it, get it done manually? This is a small problem. By trial and error, you can get the answer here. But think of a scenario where you have hundreds of jobs and hundreds of resources to be mapped. How to do it? At least such, I believe you will also accept that these are the challenges, intellectual challenges for solving problems. Again, let us go back to our independent set problem. Here, this bipartite matching problem, if we can reframe it in such a way like this, for each possible mapping, we have one edge, like X2, Y1, X2, Y2, two edges. So there's a possibility X2, Y1 and X2, Y2. We'll have each possibility is represented by one edge. So now you construct a graph where each such edge is a node. So number of edges or number of mappings of bipartite graph is the same as the number of nodes in my graph. Now, I have to construct the edges. How do I do that? If we consider two nodes, any two nodes of that graph, I know what are those two nodes are. If these are edges, if these two edges, if every edge has two nodes associated with it, like X1, Y3, or say X2, Y1, it is a mapping, but it has two nodes because it represents an edge, X2 and Y1. And each such node of that graph will be like this. Now consider any two nodes in that graph. If the edges corresponding to those two nodes does not have any node in common, consider other way around. If those two nodes are such that the corresponding edges have at least one node in common, then you draw an edge. Say X1, Y3 will be one node there, and X3, Y3 is a mapping. You have a node there also. So the mappings corresponding to those nodes have one node in common in the bipartite graph. So we draw an edge. But if we have a node corresponding to X2, Y1 and the other one corresponding to X1 and Y3, they do not have any node in common, the corresponding two edges, then there is no edge in my new graph. So this is how I build the graph. The mapping, each mapping is represented as a node, and any two nodes will have an edge if and only if at least one node will be common in that corresponding to edges. Now I complete this graph and convert this bipartite matching problem to that graph problem. And here is the beauty. What is maximum independent set in that graph? It is the solution we are expecting. Because these are the mappings, and no two of those mappings have any node in common. That is the beauty of computing. I'm not saying computer science. That is the beauty of computing, beauty of algorithms. How do you convert the one problem to another problem, which apparently do not have, seems to be completely unrelated. But how do you convert one problem to another problem for which the solution already exists? Okay. I think I can go ahead for another 10-15 minutes because it's better to carry on with the momentum. And I do firmly believe that you are enjoying.
Yes, sir. Please, sir.
Okay. Next, another problem. Here, I've deliberately chosen this problem because at least one problem, I want to take you to the conclusion in terms of design of algorithm. So far, we have concentrated on algorithms for conversion of the problem to a model. Now, we'll go right up to the solution level. And this is a very famous problem known as Dijkstra's algorithm. If you remember, we have used the word Euclid's algorithm somewhere. So these are the names you must remember. Like if you are a student of physics, you must remember what is Newton's laws of motion. If you are a student of chemistry, you have to remember what is Charles' law, Boyle's law. These are like that. This is known as Dijkstra's algorithm. Now, there are many ways of solving this problem. We are just using the shortest path problem. Shortest path means, okay, here is a graph, A, B, C, D, E, 5 nodes, A, B, C, D, E, 5 nodes, and the edges means the distance between any two nodes. A to B is 4, B to D is 2, C to B is 1, something like that. Something like that. The problem is from node A, I want to compute shortest distance from to each of these 4 nodes. Shortest distance from each of these nodes. The students of MAKAUT can take it as a problem. You have MAKAUT office in Salt Lake. Probably you have hundreds of engineering colleges. So from MAKAUT, what is the shortest route by distance to each of these engineering colleges? How do you compute that? You have the road network, you have the graph in front of you. What are the roads available? There could be one ways also, like I have given C to B, B to C, one way also. And you know the distance also. You can go to Google and get the distance. So, absolutely useful, so useful. You have MAKAUT, look at it somewhere. You have hundreds of colleges placed all over our state or whatever. Very often you have to communicate to each of these colleges Sometimes you have to go by road also. Everything cannot be transmitted electronically. So from MAKAUT, what would be the shortest path by distance to each of these colleges? Okay, how do you do it? We start from A. Again, listen to me very carefully. Don't miss a single word. I start from A. So step 0. Step 0 means I am starting from A, and from A, I have direct path to B and C, and I do not have any other path. So A to A would be 0, obviously. Distance from A to B will be 4. Distance from A to C will be 2. And D will be infinity because there is no direct path from A to D or E. That is step 0. Now I come to step 1. From the previous step, I see which one is the closest node to my original node. What is this? In this case, C is closest because B is distant 4, C is distant 2. Okay? So now I add, and whenever I get such an identified closest node, these I include in the list of nodes I have already traversed. To start with, I had only A. Now we have A and C both because I have traversed up to C also. Now check for all other nodes in the graph and find which one is the shortest from either A or C. We have A and C now in my already covered nodes. Now from C, B is 1. From A, B is 4. So this is 2 plus 1, 3. But this is 4. So after step 1, my B was 4, but now my B becomes 3. Rationale is from A, if I have to go to B, I will go via C, and by that process, the distance will be less. So we start with one node, keep on traversing. At every step, we add another node, which already has traversed. And at every step, considering all the nodes which already I have traversed, find the nearest, shortest nodes. So from C, and the logic is simple. In step 0, I would have gone to B from A. Now we'll go via C. I'll gain 1 unit. And now since C I have already traversed, C to D is 4 and A to C is already 2. So 2 plus 4, D will be 6 and E will be 7. Why? I am computing distance from A. 6 means from A, not from C. From A. A to C already takes 2 and C2 is 5. So E becomes 7. So now next step, C is already there. Now I include B also. If I include B now I have A, B, and C. Okay? In step 1, D was 6. In step 1, D was 6. But now, now I have A, B, C all together. So if this is together, I can go to D via B, because B is now within my set of traverse node also. So it becomes 5, because 3 up to B and add 2 more to go to D. Okay. So by adding just C, by adding C in the previous step, I have reduced the distance of B from A. By adding B, I have reduced the distance of B from A. And in step 3, now D is also in my traverse list. And I go on like this. And finally, this is the answer. From A, how do I get into this, the shortest path to all the nodes? Remember, what are the characteristics of an algorithm? Input, output, finiteness, definiteness, effectiveness. In this case, input is there, output is there, all the secret, and each step is finite, each step is definite, and each step is effective. But all we have to know, all we have to do is whatever we have said right now, we have to write it down in unambiguous statements in the form of a statement. And this gives you the algorithm. This gives you the algorithm. So algorithm to compute shortest path by Dijkstra's algorithm. This is how we have to do it. And we have to remember that it has to be generalized in the sense that it should be valid for all n, whatever large n may be. And I've included this problem once again deliberately to explain one more characteristic of such problems, which is known as memoryless property. What is memoryless property? In generalized terms, if I, A, B, K, etc., J, these are the nodes, I, A, B, K, J, all these are the nodes. If all such sequence of nodes represent the shortest path from I to J, if all these sequence of nodes represent the shortest path from I to J, and K is any intermediate node in that path, K is any intermediate node in that path, then I, A, B, K will be the shortest path between I and K. Again, so from I, if you somehow follow the shortest path to K, you can follow the remaining shortest path. You don't have to remember that. So this is known as the memoryless. This is known as memoryless property. This is Dijkstra's algorithm. In next classes, we'll do some other, we will take care of some other algorithms. Let us take another problem. This is the last problem for today. I thought of concluding this with this very famous problem in computer science. Suppose you have a two-dimensional map. You have a two-dimensional map, maybe very complex. And you are given n number of colors, as many colors as you want to use. You have to color the map in such a way that no two adjacent regions are of same color. Obvious. Intuitively obvious problem. Once you color a map, whatever be the complexity, may have, say, USA has 52 states, India has 32 plus 7, so many states, whatever. Europe, I don't know how many. So it's a two-dimensional map, and you are given, say, 10 colors, 20 colors, how many colors you want. And you have to color each region in such a way that no two adjacent regions can have the same color. The problem is, what is the minimum number of colors you need? The problem is, what is the minimum number of colors you need? At the beginning itself, I told you what algorithm does. Essentially, it changes your mindset to handle any problem rationally, logically, and analytically. In this case, this mapping problem, like in other problems also, if you start working on it manually without thinking at all, can you imagine what a mess it would be? And the problem is, you have to color it with minimum number of colors. And again, here is the beauty of modeling. We are trying to convert this map to a graph. How? It's intuitively obvious. Each region happens to be a node of the graph. Each region happens to be a node of the graph. And any two, I don't know whether I missed out anything, any two nodes will have an edge if they have any boundary in common. Like region 1 is adjacent to 2, 3, 4, 7. Oh, sorry. There should be an edge between 1 and 2. It got, it got erased inadvertently. There has to be an edge between 1 and 2. Sorry, please add an edge between. It got erased finally when I made the final cut. So 1 is adjacent to 2, 3, 4, 7. Say 3. 3 is adjacent to 1, 2, 6, and 7. So this is how we convert this. This is how we convert this map into a graph. And now my problem is to attach colors to the nodes in such a way that no two adjacent nodes has the same color. Same problem. We convert this map to this graph. Again, apologies. There should be an edge between 1 and 2. I may have missed out something also, but I've given the logic. So, from graph theoretic model, the problem is to attach color to each of these nodes in such a way that no two nodes, no two adjacent nodes will have the same color. This is known as a map coloring problem. It has been conclusively proved over the years that you cannot do it in a way better than 4 number of colors. This is known as a 4-color problem. You cannot do it in 3 colors, 2 colors. Minimum color required is 4. Recently, there are some research studies which claim that you can do better. But forget it. We need not have to be that updated. But this is famous 4-color problem. Again, the idea is to convert an existing problem to another model with whom we are comfortable and we have the results derived out of that. And how and what is the algorithm to convert the problem, existing problem, to another problem. Okay. I think, Prem, are you there? Okay. So I think we are done today. Again, if you have any questions, welcome. I would strongly suggest to mail or submit the questions to the to MAKAUT, who is basically coordinating the series of sessions. I'm expecting plenty of questions on today's topics, if you are interested. So it will be collated in the coordinator's room. And in the next class, to start with, we will analyze those questions, because I do believe that the question may be raised by one person, but deliberations, everyone should have the opportunity to participate. Okay, it was very heavy today. Prem, are you there?
Yes, sir.
So I think that's all for today.
Yes, sir. Yes, sir. We may close it because we are not getting the question in the chat box. So probably your way of teaching is understandable for us.
Yes, yes. So I hope we have got enough food for today's menu.
Yes, sir. Yes, sir. Your the way of teaching is very much simpler. Yes, sir. And they are getting all the things easily, sir.
So,
but also, sir, if the participants have any questions, then please feel free to write.
Maybe in the next class. Huh? I'm feeling very tired. It was very tiring. Yes. But remember, don't try to jump into 5th floor. You have to build up your case. Okay? Prem.
Yes, sir. Yes, sir. Yes, sir.
That's how we are moving.
Yes, sir.
I will end with that again on a lighter vein. सुना है ना मन्ना दे का famous song लगा चुनरी में दाग.
Yes, sir. Right, sir.
Remember last 3 minutes. वहां पहुंचने के लिए आपका पहले 7 मिनट जरूरी है.
Yes, sir.
Okay.
Yes, sir.
So gradually we are building our speed. Okay. And but we got to be very careful. You have to understand every word, every sentence I am saying. Every word and every sentence I am saying. And I would strongly suggest, mainly the computer science and IT students who are also in the theories, and more so who are interested in theory of computer science, you must be having a formal course on design and analysis of algorithms, which I used to teach for the last 20 years. I'm not getting into that there because that's already there in your curriculum. And at least the books by Corman, Klein-Bach-Tardos, and Horowitz Sahani. These 3 books you must have access, and the problems I have referred to will be there at least in one of them, if not in all of them. But they cover that as a, theoretical computer science kind of thing. So you can get details over there. So that's it. And Prem, next Thursday, 11 o'clock.
Yes, sir. Yes, sir. Sure, sir.
And today's whatever this we had this
Yes, sir.
participants.
Yes, sir. Whatever
Send
the
the
links as you have provided me, I will look into it, sir.
Okay.
Yes, sir. Yes,
And
sir.
send me your just WhatsApp me your number so that I
I
can
will mail you,
also.
sir. I will mail you, sir. Yes, sir.
Okay.
Yes.
Thank you all.
Thank you, sir, for this session. Thank you all participants for joining the session. We will be back in the next session that will be on next Thursday at same time. Thank you all. Thank you.
Thank you.
Thank you, sir.